Welcome back to this course on ILP, DLP and TLP. In this lesson I will describe Tomasulo's algorithm and how it implements dynamic instruction scheduling. Before I describe the details of Tomasulo's algorithm, I will describe the basic idea behind dynamic scheduling. Here are three MIPS instructions: a divide double, an add double and a subtract double. There is a data dependence between the divide and the add double, since the divide writes F0 and the add reads F0, as indicated by the red arrow. As before, I assume that floating point divisions take 20 clock cycles and are not pipelined. Then this pipeline diagram shows how the instructions will be executed on the pipeline processor with multi-cycle operations. The first instruction incurs no stalls because it is the first one. The add double stalls for 19 cycles in its decode stage because it is data dependent on the divide. And because the add double stalls in its decode stage, the subtract also needs to stall in its fetch stage. The main point of this example is that the subtract is stalled even though it does not depend on any previous instruction. The basic idea of dynamic scheduling is to get rid of such stall cycles by allowing instructions to execute out of order. There are also some stall cycles caused by a structural hazard if there is only one floating point adder, but they are not the main focus of this lesson. So if instructions are executed in order, there will be many stall cycles as illustrated in this pipeline diagram. And the basic idea of dynamic scheduling is to get rid of these stall cycles by allowing instructions to execute out of order, as this pipeline diagram illustrates. In this execution, the subtract does not stall, but it is executed while the add double stalls. An analogy can be drawn between dynamic scheduling of instructions and roads and cars. In an in-order processor is like a road with one lane. If one car stops, all cars behind it have to stop also. An out-of-order processor, on the other hand, is like a road with temporarily multiple lanes. If one car stops, the cars behind it can take over. I will now describe Tomasulo's algorithm. This is a picture of Robert Tomasulo, the man who invented the algorithm. In 1997 he received the Eckert-Mauchly Award, which is an important award in computer science, for his ingenious algorithm. If you have an algorithm named after you, you made it in this field. Unfortunately, he passed away in 2008. Tomasulo's algorithm was implemented in the floating point unit of the IBM 36091 processor, even before caches were invented. The goal was to achieve high floating point performance without having to develop a special compiler for the 36091 processor. IBM wanted to use the compiler developed for the entire 360 family of processors. The 36091 processor had a number of limitations which made it difficult to achieve high floating point performance. First, it had only 4 double precision floating point registers, which limited the effectiveness of compiler scheduling. This motivated Tomasulo to find a way to get more effective registers, and he did that by implementing register renaming in hardware. In addition, the IBM 36091 had long memory accesses and long floating point delays, which Tomasulo's algorithm was designed to overcome. The IBM 36091 is a prehistoric processor, available already in 1966. So you might ask the question, why should we study a 1966 processor? Well, the answer to that question is very simple. All modern desktop and server processors are based on Tomasulo's algorithm. The Intel Core processors, the IBM Power processors, etc. To understand their architecture and organization, we need to study this algorithm. Now I describe some key hardware structures used in Tomasulo's algorithm. Here's the same example as before. We want to allow the subtract double to proceed when the add double is stalled. To be able to do so, we need to get the add double out of the way, so to speak. In other words, we need to buffer the add double somewhere. In Tomasulo's algorithm, these buffers are called reservation stations. Second, when an instruction is buffered in a reservation station and its operands become available, the reservation station needs to be informed of that so that the stalled instruction can proceed. For that reason, in Tomasulo's algorithm, the results produced by functional units are broadcast on a bus called the Common Data Bus to all reservation stations. This brings me to the pipeline phases of Tomasulo's algorithm. I purposely say phases rather than stages because pipeline phases may take several clock cycles, whereas a pipeline stage always takes a single cycle. The first phase is the instruction fetch phase. In this phase, the next instruction is fetched, but not in a single pipeline register, but into a FIFO queue of pending instructions. The second stage is the issue phase. In this phase, the next instruction is retrieved from the instruction queue, and if there is a free matching reservation station, the instruction is placed in that reservation station. If there is no free matching reservation station, then we have a structural hazard and the execution has to stall. Furthermore, if the values of the operands of the instruction are currently available in registers, then the instruction is issued to the reservation station together with these values. If not, the operand values are currently being produced and the instruction issued together with identifiers of the reservation station that will produce these operands. The third phase in Tomasulo's algorithm is the execute phase. When all operands are available, meaning there is no raw hazard, and a functional unit that can execute the instruction is available, then the instruction is executed. If not all operands are available, the reservation station must monitor the common data bus for the result to become available. The fourth and final phase is the write result phase. In this phase, the functional unit writes its result onto the common data bus to all reservation stations waiting for them and to the register file. In addition, the reservation station is marked free so that it can be reused for another instruction. Now I will draw the basic structure of a floating point unit based on Tomasulo's algorithm. As explained on the previous slide, first the instruction is fetched by the instruction fetch unit into a FIFO queue of pending instructions. Then, in the second phase, the instructions at the head of the queue is issued to a matching reservation stations. Here I have drawn in total 5 reservation stations, 3 floating point addition reservation stations that can hold floating point add and subtract operations, and 3 floating point multiply reservation stations that can hold multiply instructions. As explained before, the instruction is issued together with its operand values if they are available in registers, otherwise they are issued together with identifiers of the reservation stations that will produce these operand values. In the next phase, the execute phase, the instruction is executed. In this example, the reservation stations add 1 to add 3 are connected to one or several floating point adders, and the reservation stations mul1 and mul2 are connected to one or more floating point multipliers. Finally, in the write result phase, the result is broadcast on the common data bus and written to every waiting reservation station as well as the register file. In order to keep track of the state of every instruction, each reservation station consists of 7 fields. The first field is the operation to perform, such as add or subtract. The second field, RS1, contains the identifier of the reservation station that will produce the first operand value. A value of 0 indicates that the source operand is already available. Similarly, the RS2 field contains the identifier of the RS that will produce the second operand value. The next 2 fields are val1 and val2, the value of the first and of the second operand. Note that either the RS field or the value field is valid, but not both. The 6th field contains an immediate or address. If the instruction has an immediate operand, it is stored here, and after address calculation, loads and stores store the effective address in this field. Finally, there is a 1-bit busy field that indicates if the reservation station is occupied or free. An example to make this more concrete. Suppose the instruction is an add, the first operand is being produced by mul2 and the second operand value is available in a register. Then the content of the reservation station is as shown here. The operation is an add. RS1 is mul2 since mul2 produces the first operand. RS2 is 0, indicating that the second operand is available. Value 1 is not applicable since it is being produced by mul2. And value 2 is, for example, 12.55. The immediate address field is also not applicable, and the busy bit is set to indicate that the reservation station is occupied. To track whether an operand value is available in a register or is currently being produced, each register also has an additional field RS. This field contains the identifier of the reservation station that will produce the result that should be stored in this register. This field is blank or 0 if no currently active instruction computes a result destined for this register. Here's an example. The RS field of the first and third register are blank, which means that they currently contain valid values. The second register is currently being produced by reservation station mul1, and the fourth register is currently being produced by the reservation station add2. I will now give an example of the issue phase of an instruction. As explained before, a floating point instruction is issued if a matching reservation station is available. Furthermore, if the source operand is currently available in a register, it is issued together with the operand value. On the other hand, if the source operand is currently in flight being produced, then the instruction is linked with the reservation station that will produce this operand value. Suppose now that the instruction multiply double F0, F1, F2 is at the head of the instruction queue and should be issued as highlighted here in green. The register file shows that register F2 is available and contains the value 0.2. Register F1, on the other hand, is being produced by reservation station add2. The multiply instruction will issue to reservation station mul2, for example, highlighted in green. Obviously, it performs a multiply operation. The first operand will be produced by reservation station add2, and the second operand is already available and equals 0.2. Notice also that because the multiply writes F0, the RS field of register F0 has been set to mul2 since this is the reservation station that will produce it. When all operands are available, the instruction in the reservation station can be executed. Notice that several instructions may become ready at the same time. For floating point reservation station, which one is executed first is arbitrary, but first in, first out is usual. I will make sure that loads and stores are executed in order, however. I will explain later why. Here's a simple example of instruction execution. The multiply instruction is ready since both its operands are available. So it will execute on one of the floating point multipliers and produce the value 0.85. Finally, execution proceeds to the last stage, write result. When the functional unit has produced the result, it is written onto the CDB and from there to any reservation station and register waiting on the result. This picture illustrates this phase. The instruction in reservation station add2, highlighted in green, is ready to execute. Furthermore, as highlighted in red, reservation station mul2 is waiting for this result and the result needs to be written to register F1. The subtract instruction in reservation station add2 has executed. It writes its result 2.0 onto the common data bus together with the identifier of the reservation station add2 that has produced it. The result is broadcasted on the common data bus to all awaiting reservation stations and the register file. And finally, the first operand of the instruction in in reservation station mul2 is now available and equals 2.0. Furthermore, register F1 has been set to 2.0 and its RS field has been cleared, and we end up with this state. This completes this lesson. Thanks for watching. In the next lesson, I will show how several consecutive instructions are dynamically scheduled using Tomasulo's algorithm, hoping that you will fully understand it and never forget about it. Hope to see you back.